Thank you. I always feel comfortable coming to Cal State University Long Beach. I feel welcomed here. And I'm particularly interested in this series that we've been giving called The Things We Ought to Know About Digital Communications. And I think it might be a good idea for me to explain how it all got started, even with that title. Notice that when I worked at the Aerospace Corporation many years ago, they sometimes would invite me to participate when they hired new people, and they wanted me to help determine their technical abilities and whether or not they should make them an offer. And in so doing, I had to come up with something in a way of asking them a question and trying to decide whether, you know, their answers made sense. And so it started off this list, which is now 6 pages long and 70 items on it, and it's still growing. It's still in a live list. It started off as a half dozen items, and it grew every year a little bit. But it turned out to be, and as you look down here, you'll get an idea of the kind of questions that are on here. You know, why is it that EB over N0 is a natural figure of merit for digital communication systems? Usually we talk signal-to-noise ratio. What's this EB over N0? Notice that the error performance of digital signaling falls into two clear degradation classifications. That's all there is. There's either some kind of a noise that's going to reduce the signal-to-noise ratio, or there's going to be distortion. And that's all you got to worry about, those two. What about digital modulation schemes? Again, notice how many things fall into two compartments. There's either orthogonal signaling, example would be Emory FSK, or the ones we're going to be talking about today, which is OFDM, or there's phase amplitude signaling. And that's all there is. I mean, that's the whole bag of signaling that there is in digital communications. And that's the sort of questions that we've come up with. Where in the system is EB over N0 located? Describe trade-off types. What about the Shannon limit? Is it something we can actually achieve? There are two phases to error correcting coding. One is good, one is bad. Describe subtle energy and rate transformations. We're going to be doing that today. And so as you go through all of these down through 70, you know, what I've come to the conclusion is being familiar with these items on this 6-page checklist will, in my opinion, put you on the road to success in this chosen field, which I think is just a fantastic, amazing field to be in. And therefore, I offer this to you as a way to, a tool to calibrate yourself. Take these 6 pages, and I feel confident if you're ever going to go on an interview for a job or such, if you can answer all of those 70 questions and are familiar with those concepts, and notice that after each one of them, I generally put a section coming out of my textbook wherein you'll find more information. Sometimes there's a reference to a paper, but most of the time, or sometimes there is no reference, but there's just a reference to the notes themselves. So again, I think it's important for you to have such a tool. Imagine me promising you that if you go through these 70 items and, you know, take 2 or 3 per day, so that wouldn't take you too long, and make sure that you understand every one of the subtleties and explanations about every statement in there, you're going to know an awful lot, and it's going to be a wide swath of information across the board. And you'll be relatively prepared to answer what any interviewer, at least these are the ones that I came up with as an interviewer over several years. So I offer it to you. Now, the first 4 parts, remember we went through many of these fundamentals. The big picture, why digital, Nyquist and Shannon, what do they teach us? Bandwidth efficiency, bandwidth limited and power limited systems, turbo and LDDC codes and so forth, and fading channels was the last important area, and a lot that we're doing today depends upon understanding fading channels. We'll sort of remind you a little bit as we go on. But so part 5 is on OFDM and single carrier OFDM. So everybody, I think, who is familiar with my book certainly knows the picture on top of the book, my signature slide. And today, if I were to make a new revision of the book, that signature slide would have to have at least 2 added functions, and that is the OFDM and single carrier OFDM in light green, and of course the MIMO, which is going to be part 6 of our series as well. So on this slide, what you see is that we really have a whirlwind tour of OFDM today, because remember what we're out to do. My charts tend to be very busy with lots of information. We obviously can't teach a short course in a couple of hours in such busy charts. So they're mostly for you to take home and reference. But what we want to leave you with is a big picture, a sort of an intuitive idea. There are just really a couple pictures that I want you to understand well. And when you do, because I've had students already say to me, that picture, that gave it all to me. I don't need any more. That picture did it. And so we want to leave you with an intuitive sense. And so remember what OFDM does. It elegantly, and let me underscore that, it elegantly overcomes the adverse effects of the bad things that happen in a fading channel. Frequency selective fading and fast fading. If you were here last time, you'd know that. Well, what made me so excited about OFDM a dozen years ago was this newspaper clipping from, just about 12 years ago, when it was announced in San Diego that Qualcomm Corporation has just purchased a company which is called Flarion, and the Qualcomm Corporation, they basically invented CDMA in IS-95. They came up with the basic direct sequence type of modulation, which is used today all over America as the primary spectrum technique for mitigating against fading multipath channels. And I thought that was wonderful, and a very clever idea of the rake receiver. So if Andy Viterbi, the head of this company, went out, the head of Qualcomm, went out and bought another company simply because they had a handle on orthogonal frequency division multiplexing and multiple access, then I figured this has got to be very important, and indeed it was. For those of you who think that this just came about a dozen years ago, that's not true at all. Notice that the history goes back to 1957 when Kinoplex came along. Then there were these 19-inch rack-mounted panels, and essentially, and I want you to please note that even though that was born, Kinoplex was born in 1957, it was a method for sharing the channel's bandwidth. It was not a process to invert the effects, those bad effects of the channel as we use it today. So we're not just looking for another sharing bandwidth scheme here. It's got a lot more magical qualities in simply precluding the bad effects that we might see from a multipath situation. The big picture about OFDM is it's got a shotgun approach. So Sharon Langton, who I knew her when she was at the Ford Corporation in Upper California, and she's got some nice websites with these little schematics to show you how it's an ordinary faucet that has water coming out of it versus a shower, or a big shipping truck versus a lot of little ones. And you see the whole idea of the shotgun approach, as it is in FDM or FDMA, is we're going to partition a high data rate signal so it can be sent over many low rate channels. And the whole idea is if you do encounter some kind of an accident along the route, and if it were one large truck, the whole cargo would go down or would be delayed. And here it's just 1 or 2 or 3. And that's why we have error correction coding. Anyway, when you take a look at single carrier systems. If you have a wideband signal, notice you have very short symbol times. Short symbols equals large bandwidth. And the moment you go to a conventional multi-carrier system, this is not OFDM, this is just anybody sharing the bandwidth by giving different segments to different channels of different users. What you have are longer symbols. I mean, you're sending things out slower, a much longer time, because each one of these transmissions represent a lesser amount of bandwidth, so it's slower. And so, but the whole beauty of OFDM, when you compare it to a conventional system, is that in a conventional system, you got to have some spacing, some little guard bands between users that they don't interfere with one another. But the O in OFDM is what gives us the magic of being able to squeeze them together so tightly with a 50% overlap and a factor of 2 improvement immediately without doing anything else, just by insisting that they are orthogonal to one another. So one might ask the question, well, why don't we take ordinary radio like AM and FM, and instead of doing it this way, hey, why don't we take ordinary radio channels and overlap them and then get twice as much spectrum capability? And the answer on this next page is the height of it is that the simplest way to assure orthogonality of adjacent sinusoids is to have all the sinusoids have an integer number of cycles per fixed interval and have constant amplitudes over that interval. And that's very difficult to do in a wideband system. Just these are simple rules that are simple to follow when you got a low bandwidth or, just a subcarrier that's just got a tiny bandwidth. We can follow these rules and make this happen, and it doesn't happen. It can't happen that easily in a wideband system. This is just a reminder for how we test for orthogonality. We can do it either in the time domain or the frequency domain. It's certainly easier to see if you have signal 1 and signal 2. What does it mean to be orthogonal to one another? Well, a cinema might be can't possibly interfere with, don't exist in the same time or in the same space. And seen as vectors, they're just mutually perpendicular to one another. So there's no crosstalk. A projection of one vector upon another is a zero projection. And so, and mathematically, the way we see that is we talk about the inner product averaged out over a simple time, or the correlation point. This is a point, and that is you take S1 and S2, and you just put them one on top of one another, you multiply them, and you average out the result, and it should average out to be 0, and that's our little test. We can have the same thing when it comes to tones. You're looking at the spectrum of any particular tone that we're talking about. It simply has a sin x over x appearance, and if you ask, what is the smallest tone spacing, let's call that delta F, to maintain orthogonal signaling, it is 1 over the time duration of the tone. 1 over the time duration is simply the speed of the tone. So this distance here, and notice what it does on the picture. It corresponds to the point where on tone number 1, the peak value corresponds to what is a 0 value at tone number 2. So you sort of get a feeling that there's going to be no correlation, a 0 correlation. So notice what you really need. All you need to know the smallest tone spacing is the symbol speed. So if I ask you, if I have 2 tones, 10,000 hertz and 12,000 hertz, and I ask you, are they orthogonal to one another? Anyone? Well, if you tried to answer me, you would be incorrect even trying to answer me, because the thing you've got to know immediately is how fast are you signaling? Because just to say 10,000 hertz and 12,000 hertz describes, how many cycles there are in the interval. But what you see, in order for them to be orthogonal, the spacing has got to be equal to the speed at which they're being delivered. Okay, so remember, this is an important slide to emphasize the fact that long pulses are the key to OFDM. See, what we do when we take a large bandwidth signal and we partition it into lots of little subbands is we're making the pulses of each one of them, we're lengthening them, and that is the key to what we're doing. And so let's follow that again. And you see, for ordinary conventional multi-channel systems where there's a little bit of spacing between them for safety, over here there's this 50% overlap, which gives us this factor 2, and you can see immediately that corresponds to an improvement in bandwidth efficiency. I basically can squeeze everything down to 1/2 and get the same bits per second that I had in the conventional system. And you might remember that's what I called a metaphor of the metaphoric black cloud in any fading channel. That is, when a vehicle is or a pedestrian is moving along in a fading wireless communication system, he's always, surrounded by this kind of an overview where listed here is the channel gain, or think of that as the quality of the channel. And what you've got are these the severe ups and downs in the quality, and the two important characteristics which we went over last time is the coherence bandwidth and the coherence time. And you see, basically what it's looking for is this is not rocket science, but you see the region here where this thing is up and comes down. This region in frequency is saying this is the region of spectral lines, and that region or signals having spectral lines in this region are going to be treated at the receiver in a highly coherent way. That is, when you signal, let me just go over it one more time. For f sub 0, the coherence bandwidth was this. Well, let's move on because I have slides that describe it. But so keep in mind that in a fading channel, these are two important characteristics: coherence bandwidth and coherence time. And so again, you see that what we're doing here is we've got a situation where the channel quality is going to suffer some ups and downs, and it's not rocket science, but the region where it's up for a fair amount of time is basically telling you, well, how much time appears to be such that the signal is being received in a coherent way, in a reliable way. And the f sub 0 says, and similarly, when you get the same sort of region going this way in the frequency domain, you're asking the same sort of question as, what the spectral regions, what is the size, the chunk size of the spectral region that is either fading or not fading, but behaving in a like manner, in a coherent manner means in a like manner. And so notice, and essentially what we're going to be doing in OFDM is we're sort of taking a slice and looking in this direction. And what we're seeing is that any one of those slices is going to have an amplitude value, a quality value of that channel, which can be thought of as approximately flat. Because there's, you see here, you wouldn't think of it as flat because of this large excursion it's going through. But when we're taking little sub-channels in there, it is flat. And that's why we often use the same picture that came out of the MIMO section that says it fits nicely into our assumed MIMO channel model, narrow band flat fading channels where received phasers can be described with complex value gain factors. By the way, I think this picture also leads us to see what we're gaining with OFDM. We've got some fairly complicated transforms. That is, they look complicated to the human eye. Actually, it turns out to be the simplest mathematical way of doing this narrow band flat systems. But what does it buy us? What is it buying us? And here's where you can see what you're buying us. Look what you want to do when you say the word equalize. Equalize means that the frequency lines are, although they left the transmitter in what we call a perfect or near perfect, flat, equal intensity to all of the spectral lines, look at how they arrive at the receiver, mostly, well, through some circuitry effects, but mostly through multipath effects. And so immediately before anybody ever heard of OFDM, the way we treated that was with equalizers. And what we've now done is we've made the task of equalization simple, because it is nothing more than a simple product scaling in the frequency domain. We are multiplied by a complex number so that every one of these come out to be the same and normalized to some flat response. So that's in the big picture of what we're buying with this transformation computations, Fourier transformations, in order to buy ourselves simple, inexpensive equalization. So what is OFDM? It's a multi-carrier transmission system with orthogonal subcarriers, where we're going to take a high-rate signal and it's going to be partitioned so it can be sent over many low-rate channels. And to avoid frequency select fading, the bandwidth of each partition needs to be less than the channel coherence bandwidth, and I'll review some of that with you. Okay, so if you take a look at a modem, and in this particular modem, what we call sigma sub tau is known as the RMS delay spread, and it's given to you in terms of microseconds, 3 microseconds. And notice how easy it is to change that delay in terms of symbols, because if I simply divide the RMS delay spread by the symbol time, or multiply by the rate, you see I'm multiplying, if I'm multiplying sigma sub tau, which is in seconds, multiplied by a rate is symbols per second. Notice that the seconds cancel out, and I'm just left with symbols, and the answer is that in this particular example, 3 microseconds is the same as 2 symbols. And here is an example of the as you see on the title here, what I've put in, the effect of lengthening the symbol time. That's what OFDM is all about. You see, without OFDM, I put you through an ordinary little example. You can follow this on your own, of 1 bit per second, 1 megabit per second, and the time is 1 microsecond. You got a rate 1/2 code. You got an A to E PSK. You got symbols coming out of here, which is 1.5 microseconds, and you got this kind of a this is the RMS delay spread. So in some averaging sense, the sigma sub tau is 3 microseconds, or 2 symbols. And you can see here what we mean by 2 symbols. It means that you got the, in some RMS fashion, not the maximum value, because the maximum value would take you out here, but in some RMS fashion, this is about how you affect the received sequence of symbols, 2 of them. But look at what happens once you go into an OFDM. With OFDM, when you have lengthened, that's the whole idea, you've lengthened the symbols. They're no longer this, but you got the same environment, you got the same multipath environment, so you got the same sigma sub tau, and lo and behold, this is the bottom line of what we're trying to show you. With the lengthened symbols, the same sigma sub tau without OFDM that would have hit 2 of the symbols is only hitting 3% of 1 of the symbols. So the whole idea is to just get an appreciation here of this. This is almost like a wipeout, or a very difficult equalization in a non-OFDM case. And here you just got, listen, the worst case is just leave a space, and you've already fixed that problem. So this is the big picture about how OFDM and its lengthening helps us out. So I do want to say a little bit more about the coherence bandwidth and the coherence time, and its relationship to the RMS delay spread. Notice there are 2 researchers. A very early one is a very famous researcher in cellular telephony, W.C.Y. Lee. His publication in 1989 gave rise to what we call a coherence bandwidth, which is called a 90% coherence bandwidth, and it's very restrictive. But Rappaport came up with a less restrictive one called 50%, and that's the one you see here. So to get an understanding what this means is, and this is where we're focusing our attention, but if you don't happen to remember what the coherence bandwidth is all about, let me show you that. First of all, our picture is from the Proakis textbook, where we're looking at 1, 2, 3, 4 correlation functions, and this is the called the spaced frequency correlation function, and what that really means, the space frequency correlation function, is when you take you're looking for the effect of the channel on the spacing delta F. And what does that mean? It means that you're going to send out two tones, F1 and F2, and at the receiver you're going to independently receive each one of them with some complex receiver like getting amplitude and phase, and you're going to correlate how well do these two tones that were separated by delta F, how well do they correlate? And Mr. Lee said, you know, to get an important correlation bandwidth, you ought to use 0.9 or 90% as the metric. And Rappaport says that's a little too restrictive. Let's use 0.5, and let's call that correlated. So his correlation bandwidth is dependent on a less rigid correlation. So again, you're saying, like, look, if there is zero difference in delta F between the two tones, you get the peak value. When delta F goes a little bit positive or a little bit negative, you get a reduced value. A little bit more, and it's reduced still more, and so forth. And so you see, as you're separating in frequency, 1,000 versus 5,000 hertz, 1,000 versus 10,000 hertz, 1,000 versus 20,000 hertz, you know, that's how you plot that curve. And of course, this happens to be the Fourier transform of what we call a multipath spread. And that's probably what you're used to thinking about the moment you hear multipath, is you get fingers of return that are, these are echoes that are delayed. And these two are Fourier transforms of one another. And of course, we're focusing our attention right here on F sub 0, and I've just explained what that means. So on this slide, what you see is, let's take a case of the kind of inter-symbol interference you're going to get with no FDM and with OFDM. So if you have no FDM and you just have symbols coming along, which I'm showing as impulses right here, but the impulse response of the channel is hurtful. I mean, it's something that is going to smear. That is, every one of these, every time you're making a transmission, you're convolving it with this response, and sending out three impulses at the receiver looks like this. And of course, the receiver doesn't know the anatomy of all this. It just gets the superposition of all that value, which is a smear. Smearing is hurtful. But notice with OFDM, the whole idea is that instead of having all these smeared run on top of each other, you do get a distorted symbol. I mean, there's a rise time up here and a fall time here. And so notice that but we can fix that. And notice how simple it is to fix that. We just take the transmissions of these, remember, these are longer pulses now. That's what we're buying with OFDM. We're buying longer pulses, and there is this little space or zero space between them. But look at how we fix it. We just separate them with a guard band, and you see that the distorted part falls in the guard band, and we have just fixed the inter-symbol interference. But we're going to go further than that. You see, we introduce what is called a cyclic prefix, and that fixes things further. I don't have to fix the inter-symbol interference any further than that. I mean, once I've opened it up so that there's they don't sit on each other, it's gone. But what the cyclic prefix does is here's what it does. It mitigates signal dispersion but this is the important thing it does. It maintains orthogonality amongst the subcarriers, which are prone to lose their orthogonality as they're going, as you're transmitting them. So remember what a cyclic prefix is. It's taking the back end of a symbol and moving it up to the front end and filling up this space. And of course, that's the part that gets thrown away at the receiver. So by throwing it away, you can't right now appreciate anything more than the fact that even if I didn't have a cyclic prefix, this is not used in here. This is thrown away in here. Why did I need the cyclic prefix? The cyclic prefix really doesn't do much for the inner symbol interference, but we're going to show you how much it does for the maintaining orthogonality. Okay, so the interval fixes ISI, but it's the cyclic prefix that fixes ICI, which is intercarrier interference. So let me give you a quick preview. Remember I said to you that there are just a couple pictures that are going to drive the whole thing home, and this is one of them. My son did this, and he's always telling me, don't talk about me in your classes, but I always do, because I'm proud of him. And he came up with a picture which I think is very intuitive about understanding the formation of what's happening. And what I'm forming out here is, after all, I'm going to get a series of time points out here. And this is the output here. And if I told you this came from the superposition of subcarriers, I mean, it's hard to see just by looking at these points. So this is what my son came up with, and I think it's very useful. First of all, you've got a source of data. Most of the time, the data is going to be from some amplitude phase modulation, such as QAM is the preferred modulation in this case. But we're going to take a very simple one, BPSK. That is and here they are. D0 is -1, -1, D0, D1, -1, -1, D2, D3, +1, +1. So we got basically phasors that are either going to be positive or negative. That's the modulation. So they come in series, and the first thing you do is you go series to parallel, which now the number of wires that that are located here corresponds to the transform size. After all, we are going through what is called an inverse, and sometimes we call it FFT, and that's not really accurate because FFT is an algorithm, but I apologize for the fact that there's a mix of these notes. IDFT and IFFT in my notes are just used interchangeably. It's wrong, because IFFT or FFT is a way to implement a mathematical transformation. But the transformation is what we want, and that's IDFT or VFT is a transformation. So in this case, let's make, and notice what we're doing with, so we've got these 4 wires. They contain 4 phasors. Think of us being in the frequency domain with phasors, and that's why the transform that we're going through is an inverse transform, because we're going in with frequency models and coming out with a time domain. And so notice what we're doing. We're essentially multiplying by, notice N stands for subcarrier coefficients. So the coefficients N, you go from 0, 1, 2, 3, and you can think of that as 0 is DC. And by the way, the DC is never used in real systems for reasons that we'll talk about. But let's count it in anyway, because we have to count that as one of the portions of our bandwidth. And then there's well, when n is 1, that's the fundamental. When n is 2, that basis function is moving twice as fast. When n is 3, that's the third harmonic. It's moving 3 times as fast. So look at what happens on every one of these wires: the red wire, the blue wire, the green, and the purple. And that's what you see here. First of all, the red wire is the DC. So that's this line down here at -1. There is the DC level. And then the fundamental is the blue wire, and the blue wire is this. And by the way, the data on here, as it was with the DC, is -1. So rather than have our cosinusoid start here as it normally would be if it were positive. It starts at -1 and gives you essentially one cycle in blue. When you go down to the green wire, notice now the phasor is a +1, so it doesn't start down here, but it starts up here, and you got 2 cycles. It's moving twice as fast. And when you get to the purple one, it's also positive, so it's starting up here, and you get 3 cycles. So there is what we mean by saying that out of OFDM, what comes out of this inverse discrete Fourier transformation is all of these sinusoids are being constructed, and then this summation here represents the superposition of all of them. And so what comes out here, you think of it in terms of just collecting these points. You got +1 and +1 and -1 and -1. That's 0 for the first point. The next point is 0 and 0 and -1 and -1. That's -2. The next one over here is +1 and +1 and -1 and -1 is 0 again. And the final one here is going to be again 0 and 0 and -1 and -1 is -2. And that's how these are the 4 points, because they are simply the summation, the superposition of what's coming out. So again, what this important device is how we synthesize this output waveform. And see, you couldn't guess, could you, that this waveform that you're looking at right here represents a time samples of 4 FDM frequency division multiplexed pieces of data that are carrying 4 pieces of messages on them. You couldn't guess that that's what it is, but it's, you see, it's easier to see here that each one of those sinusoids, even the DC, the fundamental, the second harmonic and the third harmonic, they're each carrying data on them. Now you can see that data, but when you superposition them and add them up, hell, you get points. So notice the first thing that's different about OFDM, and when we get to single carrier OFDM, you'll see that in single carrier OFDM, you can actually sample the output and get your original data. Not possible here, because there's no way that the simple collection of those points can reveal what the message was originally. You basically have to go through the transformation. If there was an inverse DFT that created this, it's going to be a DFT that's going to be able to receive them. So again, there are nice pictures having to do with these formations. That is, you got basically a slab of frequency. You see, in this case, the big bandwidth was 60 megahertz. Again, you have 4 subcarriers in this place. By the way, in general, in this example, you have both a transform of 4 and the number of subcarriers are 4, but that's not usually the case. The transform size is always going to be larger because it allows for us putting in some null positions in frequency, which expands the frequency, makes for an easier filtering job. But as far as explanations are concerned, it doesn't modify anything if we make them equal. So whether it's transform size or subcarriers here, we can think of there being 4 subcarriers. You got a total of 60 kilohertz is the total bandwidth. You've partitioned it up into each region of 15 kilohertz regions, and you're looking this way, and out comes this superposition of sinusoids that we talked about. Now here's just another example where we have taken, we've got 7 the gated sinusoids stemming from such symbols. NC equals 7 here forms one OFDM symbol. So notice that when we are talking about an OFDM symbol, this is what we're looking at. This is one OFDM symbol. think of time as going to be running this way, and frequency is running this way, and there is zero frequency here, positive and negative frequency. And what I've shown plotted here is the data constellation, because at each subcarrier, positive and negative independently are sending pieces of data which represents a phasor, a magnitude and an angle from this constellation of, in this case, it's a 16-ary QAM. So I'm not going to read every word on here to you, and I'm just going to say, okay, now to show you what it looks like in time, again, I've plotted exactly what we had before. This is one such symbol consisting of 7 subcarriers, including the DC, and time is running on this axis. So again, this is how time is running, sending an OFDM symbol at each time. And when I talk about ISI distortion and distinguish it from intercarrier distortion, this is what I mean. When there's inter-symbol interference, remember time is running this way, that whatever transmissions are running this way, whatever transmission is being sent in time has the possibility of 2 of them that are nearest neighbors of doing some smearing and causing inter-symbol interference. And when I'm talking about intercarrier interference, what we're looking is at the subcarriers, and I'm saying that again, by subversion over the channel, it's possible that if I lose the whole thing is if I lose any orthogonality, I will have ICI, or I will have a distortion do that. And again, if I do not lose orthogonality, I do not have any distortion. Remember, think of orthogonality as perfectly perpendicular. That's a good geometric analogy. Projection of one axis on the other is zero projection. If you don't lose orthogonality, forget about having any ISI distortion. Okay, so we've just explained that, and we've pointed out that the guard interval alone mitigates the ISI. Just having that space is what does it. Now, we don't have to fill it up with anything, and we've still mitigated the ISI. But by filling it up with a cyclic prefix, and we haven't really proven it to you yet, but it's coming, we'll show you what that cyclic prefix does for us to maintain orthogonality. Now, in my opinion, this picture, I can't tell you how many times students who get all confused about, OFDM is very creative. Obviously, the mathematical backgrounds to make OFDM work came from some very astute ideas. And mathematicians are very interesting people. Lots of them don't have a close handle on what it takes to actually turn it into hardware and make it and apply it in the system. But they know they have something that, working with the idea of sending signals in time and representing them in frequency and having certain bandwidth constraints and orthogonality constraints, they know when they have something that's useful. And I think this picture says it all. And I've had countless times where students said, I didn't understand OFDM until you showed me that picture. And that is, I think this is a wonderful picture. Notice what we're going to be doing with this picture. First of all, the first thing it says, an OFDM subcarrier in real systems is never located at DC, even though it appears to do so in this picture. Again, for simplicity, we're just not worrying about real systems. But this is the DC right here, F sub 0. And on either side, notice that we're OFDM inputs are sinc functions. Here they are, sinc functions, representing subcarrier spectra, each subcarrier modulated with a data symbol. So again, and notice that the kind of modulation that we use for the data, if you remember from some of the earlier talks on the things we ought to know, that kind of modulation is what we call bandwidth limited modulation. anyone who's bandwidth limited wants modulation on a plane like this, because notice that bandwidth is just a function of signaling speed when it comes to that kind of a modulation. That's all it depends upon. How fast am I signaling? And so look at what I can do when it comes to trying to exploit a better and better bandwidth efficiency. Instead of having 16, I can say, let's make it 64 ARRI-QAM. That's 6 bits instead of 4 bits. Let's make it 128 QAM. Let's make it 256. Let's make it 1024. More and more and more and more bits in there. And bandwidth is not affected. Bandwidth only depends upon how fast are you signaling. That's all it depends upon. So am I getting something for nothing? Well, remember what's happening if I take these 16 points and without increasing this space, just put a point in between and make the 16 into 32. I got twice the bandwidth efficiency, but what am I vulnerable to if I just put more points in there? Double them, triple them, quadruple them, and just shove them in here. I'm vulnerable to them, or those points are more vulnerable to being misconstrued because of the noise. So I basically have to separate them. I have to make this whole plane larger, which means I have to make the signal-to-noise ratio larger. So the price I pay is signal-to-noise ratio, or power. So again, please be aware that OFDM has two kinds of modulations. It has an FSK, a frequency tones, subcarriers, that have been already described to you as power limited. And here it's being modulated with the data that's bandwidth limited. So bandwidth limited data is going to dictate an amplitude and a phase of this sync function, which is describing the coefficients of the sinusoid to be built. Yeah. I just said that. Each data symbol, here's a data symbol. Each data symbol, or constellation point. Here is, in other words, this little phasor, or this little phasor, or this little phasor. Notice this one is going to be a very small magnitude. This one is the largest magnitude over here. So the amplitude or magnitude is going to be changing, and the angle is going to be changing. So you see, each data symbol provides the amplitude and phase for forming the subcarrier. So the subcarriers are sitting at certain frequencies, but again, the rest of the knowledge needed to build that sinusoid, its amplitude and phase, is provided by the data. Okay, so remember also that for clarity, we didn't overlap these sync functions representing the subcarriers, but they would be, it would be a little too busy a picture, but it would be. And notice that the use of cyclic prefix costs time and energy and lowers the data rate and lowers the bandwidth efficiency, but use of the cyclic prefix does not affect the bandwidth at all. The bandwidth is computed, well, I'll show you later, but right over here, this is the bandwidth computation. Let's see. Right in here, we just measure. Remember, we have N sub C subcarriers. We have a delta frequency between them, delta F, just the product of those two numbers. The quantity of subcarriers, in this case 7, multiplied, or maybe it's 7 plus 1 we would use, N sub C plus 1, so that we can get a bandwidth that, you know, goes like 50% beyond here, 50% beyond here, multiplied by delta F. Okay, let's see what we're saying. So remember, we got positive frequency, we got negative frequency, and modulation with such complex signals is not unique to OFDM. The transform of any real baseband signal has what is known as Hermitian symmetry properties, but a complex signal does not, doesn't have any even or odd Hermitian signal processing. Having I and Q, cosine and sine channels, basically allows us for independent data to be sent. Did you realize that when you look at ordinary frequency modulation, what you're looking at around the zero axis are the positive and negative of exactly the same information. The positive and negative, exactly the same message. Positive and negative, exactly the same message. In ordinary telephony, when they send analog signals, or they used to send analog signals over cables, remember, they wouldn't send two-sided spectra. They'd send single-sided spectra in order to be able to save for bandwidth efficiency purposes. So we're not quite used to saying, on either side of the frequency, positive and negative, we have independent data now, not just a mirror image of the same data. So, so complex modulation, that is modulation with A plus JB, or in other words, a point from the plane, is what gives us the ability to place independent data on the sidebands around the zero frequency. Independent data. Let me show you how. And to show you how, first of all, let me remind you about this picture which we showed you before, and that is this really summarizes all of Nyquist's work. If we start off with every one of these signals are real, because on the axis that you're looking at, you see a real axis and an imaginary axis, and you only have a signal on the real axis. And let's just take an analog real signal, and when we do a transform, what we're mostly used to before we get involved in discrete signal processing, we're involved in an ordinary analog Fourier transform, which first of all puts out, again, a spectrum. And notice that the spectrum is complex. That's what's always going to happen. So a real signal has a spectral in its Fourier transform that has a real part and an imaginary part. And because it is a real signal, it has what is called Hermitian symmetry, which says that on the real axis it'll be symmetric, it'll be even symmetric. That is, everything that goes positive here will have a mirror image of going positive here. But everything that is on the imaginary axis has odd symmetry. That is, they're symmetrical, but they're with a change in sign, as you see over here. Now, when we go to sampled data, which is the one that we're interested in mostly in our business, whoops. So when you go to sample data, what you see is that you basically have analog type replications. So sampled data transformed gives you analog replications, all with the same Hermitian symmetry that we just talked about. And notice what the job of the DFT at the receiver is going to be. It's going to be to take these analog and to essentially give us samples in their place. So again, this is just, I'll let you read all the details on your own, but so even symmetry on the real axis and odd symmetry on the imaginary axis, as described here, is a real signal. If you're looking at a signal that has been multiplied by J, that is an imaginary signal, it has what is called odd symmetry, and that is that it has even on the imaginary axis and odd on the real axis. And when you take a real signal, and remember, we're looking at the frequency domain, not the time domain. And remember, a real signal on the frequency domain has a real and imaginary spectral portion. And so this is a real signal, and this is an imaginary signal spectrum. So it has, and the Hermitian symmetry doesn't change over domain. So if it has even or odd symmetry in the time domain, it has the same symmetry in the frequency domain. So again, we're looking at the spectrum of a real signal and the spectrum of an imaginary signal. So it's like taking A plus JB, and here would be the spectrum of so what we have when we are dealing with numbers like A plus JB, complex numbers off of a plane, is we have spectra that have no symmetry at all. And that's, you know, the ability that gives us the ability to put independent data on the positive and negative axis. So notice when you're looking at baseband, there's no symmetry at all. So how do you actually transmit a signal like this, a baseband signal like this? Because the moment you put it on, and what that means, let's relate what that means exactly. I mean, you can have it, you can have a signal like this, a baseband signal like this, but it just means that it is, that as a real signal, you can send it on one wire or on one antenna. It's basically got to be sent in two parts, a real and an imaginary part. But notice how by creating a bandpass signal, and that is just upshifting it up and down, then the complex baseband time signal modulated onto a carrier, real part onto the cosine, imaginary part onto the sine, thereby producing a real waveform. So this bandpass is symmetrical about zero, but has no symmetry around the carrier F sub c or minus F sub c. No symmetry at all here, no symmetry along here, but as a bandpass signal, it is perfectly, it has Hermitian symmetry. Real has even symmetry, imaginary has odd symmetry, and again it represents a transmission that can be made over one wire or one antenna. Okay, I won't dwell on this because we just have too much to cover. So let's see. Let us remember this OFDM has got to do a job for us. It's got to do a job about mitigating the mitigation. So it's been such a long time since we had that. When was it? April. I was here last, and that's when we handled the fading channels. Such a long time from April till December that I think it's useful to at least go over how we came up with a wish list. And what that wish list is it doesn't fix anything necessarily, but it gets us started. It keeps us away from the absolutely worst case type of multipath. So this is that Proacus source that I borrowed from heavily in characterizing, because I don't think there was anyone better than Proacus's book. That's how I learned everything I know about multipath, and this picture said it all to me. And again, notice what this picture is all about. It is the essence of understanding multipath channels. What you have as we go around the circle 1, 2, 3, and 4 are what we think of as various correlation functions. And in fact, we can draw a line right over here and talk about this as being the multipath spread having to do, and notice I'll ask the question later on, what determines how this changes? Can we do anything in our system to make this dying out power received echoes any different? And its Fourier transform, the space frequency correlation function, which we showed you how we were going to actually make measurements by sending out different tones that are spaced delta F apart and seeing how well they're correlated. No, we can't. It's all terrain dependent. It depends upon whether these measurements are in New York City or over the plains in Kansas or over the ocean. So it's all dependent upon the terrain. And that's this right-hand side of the picture. And what about the left-hand side of the picture, which deals with fading rapidity? Can we in our system do anything to change these pictures? And remember, these are duals. 2 and 3 and 1 and 4 are dual functions. So if I'm trying to make measurements by sending out F1 and F2 and then follow it by F1 and F3, then F1 and F4, or really send out a chirp is what's sent out of a bunch of frequencies and determine the correlation function. Here, I basically send the same sinusoid at T1 and T2, and then repeat it again, T1 and T3, T1 and T4, and view how well are they correlated as I make delta T, the time between those two transmissions, bigger and bigger and bigger. And remember what I'm looking for. Independently receiving each of these transmissions with a complex receiver, amplitude, and phase, and asking how well do they correlate. These are both correlation functions, so they're duals of one another. This is correlation is a function of sending out different tones. This is a function. This is a correlation function of sending out the same tone at different times. And you know, as the time increases, as the frequency increases, and so notice what we would like. What would we like? We'd like this correlation function to be just a flat line, or we'd like the coherence bandwidth to cover the world. You know, that regardless of the terrain, we should get a nice picture of what is an accurate picture of what's coming in, and here too, what we'd like is for the coherence time to be as large as possible, and notice, can we change anything in the system to make this different? No. The fading rapidity depends upon the speed at which this moving system, mobile system, is going. So with that in mind, let me just show you fulfilling our wish list, the starting point for mitigating a multipath channel. So now that you remember what the delta F represents, it represents separate transmissions, correlating them after I receive them at some delta F, and remember there's a 50% and a 90% definition of it, but the whole idea is that as we move through this general terrain, there are going to be these ups and downs, which remember I showed you as this metaphoric black cloud in both delta F and delta T. And what we want is for the bandwidth of our signal to fall well within this coherence bandwidth. You see what that means? Why this is a good starting point to say I want my signal bandwidth to fall well within here, because it means that every one of these spectral lines are going to be treated in a like manner. I mean, the quality or the gain of the channel is not going to affect them. They're going to be treated in a like manner. And if I had a bandwidth which was way out here, then only some of the spectral lines of my signal would be treated in this like manner, and outside of this region they'd be treated quite independently. There's the essence of distortion. When I have a signal whose behavior in spectral phenomenon is such that some of its spectral lines are having such and such gain, and other spectral lines are having a different gain, I'm distorted. So this flat fading is our starting position for OFDM. I don't want to do anything before. I don't want to try to use any diversity before I get here. And slow fading also. Remember, in the world of fading, I have this slide somewhere. I have a slide called The Good, the Bad, and the Awful. The Good, the Bad, and the Awful. And it looks like this. It basically says, on a probability of bit error curve, versus EB over N0, I'm basically going to get the good, that's AWGN type performance, Gaussian noise. The bad, it turns into an inverse linear function, and the awful is a bottoming out that looks like this. So the good, the bad, and the awful, and we're saying that the starting point should at least try to move the awful down to something which is merely bad, that is an inverse linear one, as our starting point. And that's when the symbol time falls within the channel coherence time, our signaling symbol time, and our signaling bandwidth falls within the channel coherence bandwidth. And we've showed you this slide already. So again, why OFDM? If this is the channel coherence bandwidth, and this is our signal, which is larger than f sub 0, we said only some of the spectral lines are going to be nicely behaved within here, and outside of that region, they're going to be behaving quite independently. So what I do is I partition, this is the mitigation technique of OFDM, you partition your large bandwidth signal into lots of small bandwidth onto subcarriers, and we're, see, in general, this is our going in position, which I call the wish list. The wish list gets us from here. It's not an all over fix. It gets us from here to here. It gets us from awful to merely bad. That is, I want the symbol, the symbol time. Taking the reciprocal of the symbol time is like taking the bandwidth of the signal, or the symbol rate. And I want f sub 0 to be larger. See, here it's smaller. But I want f sub 0 to be larger than the symbol rate, which in turn should be larger than the fading rate. This is my going in position. And notice how it changes for OFDM. The only thing that changes is that the signaling rate, which is like W signal, before OFDM and after OFDM, it's just been divided through by the number of subcarriers, so it's W signal divided by the number of subcarriers. So and of course we desire flat, faded subchannels. You saw this before. Again, this is terrain dependent upon where you are exactly. This is velocity dependent. How fast are you moving? And doing this is going to preclude having to worry about frequency selective and fast fading. So let's see. Okay. So if I ask the question, how large should n sub c be? What range should the number of subcarriers fall in? Well, here's our starting point. This is our wish list. F sub c to be greater than the signaling speed in OFDM. We just showed you how this is the signaling speed, which if this is the T sub 0 is the coherence time, the reciprocal of the coherence time is basically the rate in which you're going in and out of those times, or the fading rate is another name. So notice how this term here has lots of names. You can call it the fading bandwidth, the fading rate, yeah, I guess just those two, the fading bandwidth or the fading rate. So look at what I've done. I've just done a little bit of algebra. Remember, in order, first of all, I've taken the reciprocal of everything. Now, the moment I reciprocate it, then the greater than signs become less than signs, and the rest is just algebra. But I got myself in algebra has allowed me to place n sub c here to find the minimum and the maximum n sub c. And so now let's take an example. So if you assume a wireless channel with an RMS delay spread that's equal to 5 microseconds and a coherence time of 50 microseconds, and if the transmission bandwidth is 20 megahertz, find the minimum and maximum number of OFDM subcarriers needed in order to ensure flat fading and slow fading effects in order to get us into a good starting position. Okay, so here's our general wish list that we pointed out, that our signaling speed should be less than f sub 0 but should be greater than the fading rate. And with OFDM, all that we've changed is this middle term because we've got all these subcarriers and we've rearranged it, and now we're going to solve for n sub c because, after all, we have this information. W signal is 20 megahertz, and f sub 0, I gave you the wherewithal to figure that out from using either Mr. Lee or Mr. Rappaport's relationship with sigma sub tau. T sub 0 is the coherence time of 50 microseconds, and again the bandwidth of the signal is 20 megahertz. Now, before we even tell you the numbers, let me because I'm gonna ask you in a moment, of all these numbers in this example, which do you think is the most unrealistic value in what we're doing? Note that a coherence time that I've just given you of 50 microseconds is very short. All this coherent, in order for something to be coherent for that short a time, because obviously you're not standing still. If you were standing completely still, what is there in nature that is going to make that channel change into, you know, from good to bad or bad to good, either way, in 50 microseconds? I mean, seasonally the leaves rustle on the trees, and that makes some changes. There's traffic that goes by moving relatively slowly compared to microseconds. So you're going to see that that's really too short a number. And when you see what it reveals, you'll understand why. And rather than change it to a problem that's more realistic, I thought maybe you should see it. So we'll go ahead with that. So remember, this was the relationship dictated by Rappaport. That is, f sub 0 and sigma sub tau were related this way, and I had the sigma sub tau as being 5 microseconds. So 5 times 5 microseconds, and that tells me that the coherence bandwidth is 40 kilohertz, and that the n sub c minimum, remember, n sub c has to be greater than that. So my 40 kilohertz goes here, and the W signal here. So 20 megahertz over 40 kilohertz is 500. So that gives me the minimum. At least in order for my signaling, in this case, to be at a rate which is less than the coherence bandwidth, I got to reduce the bandwidth of each one of them such that it takes 500 subcarriers for such a reduction. Now let's get the maximum. The maximum says that n sub c has got to be less than, and this is where we use this number, which was very fast, which means very slow, excuse me, this is very small. It's over in a blip, and multiplied by and it tells me 1,000. Well, you know, it gives me a nice range. If I were just doing this as an abstract problem, I might not realize by these answers that something is a little wrong. So the number of subcarriers should fall in the range 500 to 1,000. That's fine. And I'm telling you that one of them is unrealistic, and I've already revealed it's the coherence time that is that short. So the coherence time is not really because. Let us show you what the velocity. See, to get a short coherence time, something's got to be moving, and it's got to be moving pretty fast. And it can be anything. It can be one of those two platforms. It can be traffic in between. It can be something's got to be moving fast. So if you just, let's take an arbitrary frequency. That's a nice round number, easy number to work with, but give us a number to play with. 300 megahertz is the carrier frequency. Then the wavelength is the speed of light, 3 times 10 to the 8 meters per second divided by 300. This is 300 megahertz. And the answer is lambda is 1 meter. And Well, what we saw from the last time I was here is that the coherence time is basically a number, this is approximate, so it's like 1/2 the wavelength divided by the velocity, and that was a given, 50 microseconds. But now solve for the velocity, and notice what the velocity comes out. In order to get that short a time for which the channel is only coherent for only 50 microseconds means something is moving very swiftly. Well, like a rocket, 22,369 miles per hour. So clearly it's not realistic. Okay, we want to talk about the importance of that cyclic prefix. I mean, we've avoided it up until now. We just said, I'll show you later, that it does more than help you with the ISI. In fact, I don't think it does very much at all for the ISI, but what it does is it maintains orthogonality, we said. So let's just take a look at that. The cyclic prefix in O at the end modifies linear convolution so that it appears to be circular convolution. So a property of the Fourier transform is that the spectral multiplication of the frequency domain characteristic of signals spectra, capital X of frequency, H of frequency, these are now continuous signals. They're not discrete. Corresponds to linear convolution of the waveform X of t with, think of this as impulse response H of t in time. But if I had to notice a property of discrete Fourier transforms, this is just the mathematics associated with a discrete transform, and spectral multiplication of the sampled signals X of k, H of k corresponds to circular convolution in time. And what that really means, this word doesn't mean much to you, but what that means is sampling the transform makes the time signal periodic. And that's what we pointed out here. Right over here, we said when we take samples, we get replicate copies of these continuous spectral pictures having a real and imaginary and having Hermitian symmetry because this was a real signal. And lo and behold, what the task of the DFT, see you do have continuous transform here, but the task of the DOT is to form samples from that continuous spectrum. So when you take a look at a sin x over x type of plot, and usually you see it on an axis that's either plotted out in time or frequency, but I'm plotted on a unit circle is a useful idea. That is, it's useful for this reason. Sampling the time signal makes the spectral transform periodic, and if it's periodic, which is easily seen on a unit circle, the transform must have stemmed from discrete samples. Now the reason it's easily seen is because notice the start equals the finish. So if you call this point corresponds to 0 here. If you call this the point where it's starting here, and let's say the time is going off this way, and it continues here and comes around. Imagine plotting it on a straight line and taking that straight line and circularizing it. In order for this not to give you a discontinuity in any way, it's got to be smooth, it's got to be equal. And so again, plotting it this way where the start and the finish are the same intercept here, you can see that going around multiple times on the circle is what dictates periodicity. So the general circular plot is one that sort of makes it easy to see that the thing is periodic. So this is what you have here are rules. These are the rules that which the the cyclic prefix is going to adhere to, that's going to give us the benefit of getting this transmission to look like it's going through a circular convolution when you send something off that is going to be operated on by the impulse response of the channel, and would, you know, your signal as it goes through the channel, you think of it as convolving with the impulse response of the channel. And there's no such thing as circular convolution in nature. I mean, you can't send something off in time and then guarantee that the end, you know, grab the beginning and put it back again at the end. I mean, there's no way of grabbing something that has been sent out already. So in nature, there's nothing that resembles circular convolution, but we're going to trick that. Remember, we said we got some electronic trickery here that's going to make it look that way. And that's what the cyclic prefix does. The cyclic prefix is a little trickery. So this is what we have to do to maintain orthogonality. Three things. Preserve the signal length. Ordinary linear convolution, if you remember, you take two things and you slide them together, you get a longer output, don't you? We need to preserve the length in order for it to maintain orthogonality. Number two, preserve the constant envelope. I'll show you examples of little MATLAB examples that I run through, that if you have any kind of attenuation in the signal that you didn't count on, you've lost orthogonality when you try to convolve these things. And preserve an integer number of cycles per gated sinusoid interval. So the if these three rules are observed, OFDM signals will experience no losses in orthogonality, and we showed you about that reminder. And by the way, I have here just a little, I'm going to go through this very quickly, just examples I've run of what we think of inner product multiplication integration, or in other words, a correlation point. If you take a 3-cycle and a 4-cycle interval, and again, you've got the equal number of cycles, exactly 3, exactly 4, and you just do product summation, and you take a look at the output at the very end, and it's 0. And you do the same thing in this case by taking, this was the cosine with the cosine, this is the cosine with the sine. You get a little different look on it, but again, you get a 0 out. Now, if you do the same thing all over again, and you have what is called a tilted cosine, as representing your signal here. In other words, it's gone through some envelope distortion, and that's one of the requirements that is going to, so that you do not lose orthogonality, is not to have any envelope distortion. And you go through the same thing here, and you get something that is not 0 on both of these. And again, and we do it all over again for what is called a match filter. That is not just not just a correlation point, but sliding a signal in, for which, when there is no distortion and you have no loss in orthogonality, the steady state looks like just a 0. But when you get a tilted version of the signal, there's some attenuation, and you do the same input as into a matched filter, and you're looking at everything that comes out. You never get to that steady state solid line. You get to a continuous little wiggle. So it absolutely, we first of all we want to take a look at how the cyclic prefix manages all these things. Starting with preserving the length, it's going to be easy to show you, and the others will too. So here's a very simple example. Here is a sampled data sequence. That is, this is 1 unit in amplitude, 2, 3, back to 2, back to 1. 1, 2, 3, 4, 5 impulses, or 5 samples of data. Let us say that the impulse response of the channel in terms of discrete samples looks like this. A typical type of a curve that simply attenuates in this exponential manner. 3 followed by 2 followed by 1. Let's convolve this sequence with the impulse response of the channel. Ordinary linear convolution. So I take 3, 2, 1. You know, with ordinary convolution, one of them gets turned around. So let's take this guy and turn it around to 1, 2, 3, and then move them in. And then do multiply and add. 1 times 3, there's nothing to add it to, so it's just 3. Then move it in 1. Now you have 2 times 3 is 6, and you add it to the next multiple of 2, so 6 plus 2 yields 8, and so forth. If you follow that completely, this is the output. The first thing that you see is that we've not preserved the length, because this was the length of the data. It was 5 units long. Here it is 7 units long. So the original 5 data samples have grown to 7. What would a circularly convolved look like? Okay, circularly convolved. Here is the, remember the impulse response, 3, 2, 1. And if I turn it around, like call it h of minus n, so call this, if this is 0, call this minus 1 and minus 2, turned around 0. And notice what I'm about to do. If you take a look at what I'm going to do, is plot it on a circle rather than on a straight line. So as I follow these index numbers, and now these are data time in index numbers. So on the outer circle, going clockwise, the values are the positive clockwise. On the circle outer counterclockwise, the numbers are positive, 0, 1, 2, 3, 4, and and clockwise they are negative, 0, minus 1, minus 2, minus 3, and minus 4. So in that way, do you see that this point can either be, when you're looking at the outer circle, positive 4, or the inner circle, negative 1. This point can either be positive 3 or negative 2. So notice what I've done here is I've taken this 0 is the same as this 0 here, but then what's sitting in bin minus 1, look, I'm translating everything to a positive bin here. I can show this at bin number 4, and this little impulse at negative 2, well, that's the same as bin positive 3, so I translate this here, and now I have a sequence which is 3 units tall, 0, 0, 1 unit tall, 2 units tall. So that's my sequence. Think of it, 3, 0, 0, 1, 2, and that's what I'm now going to convolve. So you see it over here, 3, 0, 0, 1, 2. So what I do is the same kind of product integration, and every time I move down a step, I'm going to do an end-around shift. This 2 moves up here and throws these others off this way. This one moves here and throws these off. And as I continue down here, what I get are these numbers 7, 9, 14, 14, and 10, which is the result of this circular convolution. And what did I accomplish? At least what you can clearly see, item number 1, the rule number 1, I have to preserve the length. I did preserve the length. It didn't grow to 7. It is 5 outputs that you see here. So this is just a repeat of it. This hasn't changed anything. So how can we make the channel's linear convolution look like circular convolution? The trick, this should be the word is, the trick is with a circular prefix longer than the channel delay spread. The circular prefix always has to be longer than the channel delay spread in order for it to do any good in the way of a mitigation. Making the signal look periodic. So this is what I'm going to do. You remember my original sequence was 1, 2, 3, back down 2, 1. I'm going to take the last 2 bits, 2 and 1, and move it up front. That's what we said the circular prefix does. And then I do an ordinary linear convolution with the data. I don't want to repeat the whole thing, but this is the result. This is what I get out, and they're clearly different. But notice that what I really have accomplished here. First of all, we need a trick because the signal transmitted over a channel with impulse response like this is received as a linear convolution. There is no mechanism in nature that yields circular convolution. Why not? This is my little bit of trying to get, did I do that right? No, I'm not going. From Rudyard Kipling, east is east and west is west, and never the twain shall meet. And so what I meant by that is just like Rudyard Kipling says, you know, you send out in time 1, time 2, times 3, time is time, and never the twain, you can't make early time meet late time and paste them together and show that they're the same. There's nothing in nature that resembles circular convolution. Everything that you do in the way of a radio transmission is a linear convolution. So the trick is that this cyclic prefix is a little bit of trickery that's going to make it look as if we went through a circular convolution. Because look, you saw what circular convolution did. It preserved the length. That's all you saw, and you got these numbers. And you saw that when I did this linear convolution with this cyclic prefix, I got this out of it. But notice what I'm about to do. Just as I showed you originally with OFDM, that part that is a cyclic prefix, which is some of the hash from the last transmission and some of the hash from the next transmission, are going to be thrown away. And that's to the left of this red line and to the right of this little line are going to be thrown away. And lo and behold, and remember why we're doing this, and that's to help orthogonality. What's left in the middle looks like circular convolution. The cyclic prefix has forced the linear convolution in the channel to yield the desired appearance of a circularly convolved signal. So don't you really have to hand it to the mathematicians who dreamt this up? I mean, it seems to me that it takes a kind of a special brain that has the ability to foresee what is needed to maintain a orthogonality that can be done in this manner because you want something to resemble circular convolution. Any questions? Okay, we don't. I want to save the questions for the end. How much time do we have left? Huh? Okay, I think we're gonna whirlwind finish this. Okay, so think of the IFFT as a signal generator. Constellation points. Remember, it is an inverse. And again, here is excuse me, I just didn't want to remake slides, but I'm using the terms FFT and IFFT incorrectly. FFT and IFFT is an algorithm. That's a mechanism for implementing something, a way to do it in software or hardware. But the actual mathematical transformation is called the DFT, which are the pictures I showed you, which is essentially the work that came out from Nyquist. So look at what this is probably the most important form. I mean, you do have you're going through the reverse operation here, so you have an ordinary forward FFT or DFT, but the first time we experienced this idea of instead of sampling and doing just ordinary signal processing of data with samples and correlations, we've got this FFT. It looks like a lot of hard work, but it turns out, if we get to finish this at 6:30, that you're going to see that it is the easiest way to do it. That's why OFDM resembles this transform world of mathematics. And that what it does is, remember, inverse FFT means frequency in and time out. And those frequencies, and we did in this little example use BPSK in our little example, are phasors. So remember, any plane like in QAM is a natural plane to use. So the phasor that we're talking about can come from a lot more diverse than just saying 0 degrees or 180 degrees. When you're looking at a 1024 plane, you know, you're looking at any one of 1024 of those phasors. Magnitude and angle phase would be a phasor, and that would dictate how these subcarriers are modified in their amplitude and phase. I mean, the subcarrier is fixed at a certain frequency, but it will change in amplitude or phase based on these phasors, and out come constructed sinusoids, and these are the gated sinusoids that are coming out, and we sample them, so we got sample points, and we go from parallel to serial, so we got a bunch of sample points that are coming out. And again, there's no way to look at these sample points and realize this represents the superposition of many multiplexed phases, frequency subcarriers that are each subcarrier carrying a different piece of data. Maybe an intense piece of data. After all, if 1024 it would be our type of modulation, each one of those subcarriers is carrying 10 bits of information. Okay. Okay, we talked about this already, that this is the mathematical transformation, this is the implementation, and excuse my sloppiness, but you see it throughout the notes, and I just didn't have the energy to change it. So here's a little example in 802.11a, where the uplink and downlink look symmetrical, and there are some numbers that dictate immediately that the OFDM symbol time is 4 microseconds, of which the cyclic prefix is 0.8 of a microsecond, and the data portion is 3.2 microseconds. And of course, in order to get what we call delta sub f, the spacing between the subcarriers is going to be the reciprocal of, and what exactly, one of the slides that you're going to see later on is why shouldn't we take the reciprocal of the time of the OFDM, the reciprocal of 4 microseconds? We don't do that. What we are going to use here is what we're going to call T sub s, the data symbol portion, which is just the symbol portion, the reciprocal of 3.2 microseconds, in order to form an orthogonal set. And the question might still be troubling, and maybe we should jump to answer that question right away. We can always jump away from it. Let's jump right to that question since we've just raised it now. Okay, it's right here. So right on this slide, what you see is a duration of t seconds of this. This is the data portion of the symbol, or what I'm calling, this is T sub s, what I'm calling here. And I'm saying, if I just take a look at t by itself, then it corresponds in a sinc function to where 1 over, I'm sorry, okay, I don't have the extension. Just the t portion corresponds to the first crossover as being 1 over t away. So in other words, it's like a spacing. That's how the subcarriers are going to be spaced. That's the delta f is 1 over t. And then the following page says, well, what happens if I add a little extension? And that little extension is the cyclic prefix. And the question comes up, well, this distance now is a shorter distance. It's not 1 over t now, because t has been lengthened to t sub x. So 1 over t sub x is smaller than 1 over t. And that means I should be able to get a smaller spacing here. Wouldn't that be better, giving me an orthogonal set, and it's even spaced closer together, less bandwidth? And the answer is, one might ask, with the extended length, thereby forming a family of extended orthogonal waveforms, why not do it that way? And the answer is, we don't care about it being orthogonal when it goes off in space. We want it to be orthogonal as it's being received at the receiver. So yeah, it's not orthogonal as it's flying through the air, but when it's received at the receiver and that cyclic prefix is thrown away, then you have an orthogonal set. So this is an important distinction in all of OFDM, that the spacing in frequency is not the reciprocal of the OFDM symbol time. It's just the OFDM data portion of the symbol time. Very, very, very important. Let's in fact take a little example of this one that we're working on. This shows you how, in this example, the transform size can be either you have the ability of choosing 64 or 128, while the number of subcarriers are 52, of which 48 of them are data and 4 are pilot. But remember, we said in real systems, you're always going to get an n, a transform size greater than, and here it's just slightly greater than 52, and here it's more than 100% greater than 52. It's much greater, and basically it shows you a bandwidth expansion that makes your filtering easier. And if we have time, we'll come back to those slides as well. And notice how in this case the ability to handle data rates from a low of 6 megabits per second to a high of 54 megabits per second. So it's useful to see how we would get, let's just take the lowest one and the largest one. So the lowest one would be where one of the modulations allowed is BPSK, and one of the code rates allowed is a code rate of 1. So here are the modulations allowed. Let's take this modulation and this code rate, and so this is the rate of the symbol rate. So you have, and remember that not all 52 subcarriers are carrying data, only 48 of them are carrying data. So 48 of them are carrying data, and remember it's BPSK, so it's like 48 bits that you get from here, but it's it's multiplied by 1/2 because these are code bits now. This is a coded system, so only 1/2 of them are data bits, and in order to get the bit rate, how many of those bits are you going to get when each bit, 48 times 1/2 of the bits are going off at a rate of 200 on symbols. That's 250 kilosymbols per second, and so the product of these three numbers give you the 6 megabits. And to see how that changes to 54 megabits, well, now let's take the largest modulation, 64 QAM, and 64 QAM provides this number of 6 bits in every symbol. There are still 48 symbols, and let's take the rate of the code, and the rate of the code, and now remember what you want now. You want the largest rate, because you want to go as little bit of redundancy as possible, to go as fast as possible. So it's 3/4 of 48 times 6. Again, this is the symbol rate, and the product of these numbers give you 54 megabits per second. So again, notice in a typical example all the numbers that you have here. In fact, notice this number particularly. Well, let's just go through this. What I've told you is worth noting, because you've got to keep this straight if you're ever going to get into the details. You got to segregate in your mind, give it a different name if you like, but mine is n sub c of the number of subcarriers. N is the transform size, which is always going to be larger than the number of subcarriers in a real system. N sub c is the cyclic prefix samples, N sub L, I'm calling the total of these two together. That makes for the whole OFDM symbol samples together is 80. And if you want to know the sample time, well, it's going to be the reciprocal, and it's going to be the reciprocal of the sample rate. Sample time is just the reciprocal of sample rate, which I've computed for you here. So you take the transform times the delta F, that basically is giving you the sampling rate. And notice how many ways there are. Another name that the sampling rate often gets, we call it the bandwidth of the FFT, or the bandwidth of the DFT. And you can compute it by taking the reciprocal of the sample time. You can take the total number of samples in the symbol divided by the OFDM time. You see there's multiple ways of getting at the same number called the sample rate. So let's just, in the interest of time, let's do this simple example step by step as it's called out here. Consider an 802.11 OFDM symbol system having the following parameter values. 64-point transform, that's N, with 48 message occupied bins, OFDM symbol time 4 microseconds, all the numbers I had before, 0.8 microseconds, and for the cyclic prefix, data modulation in this case is 16 QAM, and the error correcting code is 3/4. I want you to find the following: the sampling rate, the sample time, the code bits per subcarrier, code bits per OFDM symbol, the data bits per OFDM symbol, and the data rate. And also, if the channel maximum delay spread is 20 samples, determine if that cyclic prefix of 0.8 of a microsecond is long enough to mitigate the channel ISI. So let's start off. The tone spacing. Well, we said, this is what you have to remember, is that the tone spacing is the reciprocal of the time, not of the whole OFDM, but of just the data portion, which is time OFDM minus the time of the cyclic prefix. Well, we were given, basically, this is 4 minus 0.8, because it was the ordinary typical system that we saw, and we get delta F as 312.5 kilohertz. That's true for all 802.11 cases. Now the sample rate, in this case, again, we can take the N in this case. Let's choose 64, and with this delta F, you got a sample rate of 20 megahertz. Notice the moment I would, you got the ability in this case, if you wanted to, you can change to a larger transform. You can make it 128. The moment you do that, your sample rate has just doubled. You've gone from 20 megahertz sample rate to 40 megahertz sample rate. What about the sample time? Well, it's the reciprocal of the sample rate. So in this case, that's 50 nanoseconds. 16 QAM yields 4 code bits per subcarrier. So 48 message occupied subcarriers per OFDM symbol. It's 48 times 4 is 192. And now these are code bits per OFDM symbol, but with a rate 3/4 code, 192 decimated in this way yields just the data bits per OFDM symbol, 144 bits per OFDM symbol. So the data rate is 144 bits per symbol, and it's 4 microseconds if for every symbol. Per symbols cancel out, and you basically get 36 megabits per second. Now the question about the maximum delay spread is 20 samples, and the sample time you saw was 50 nanoseconds. So it's 20 times 50 nanoseconds is 1 microsecond. But lo and behold, the time of the cyclic prefix is less than 1 microsecond. It was 0.8 microsecond. If it's going to be useful, it must be greater than the RMS delay spread, and therefore we need a longer cyclic prefix in this case. Okay, we talked about this case already. Let's see. If we had till 6:30, and you have let me just repeat what the way in which you can get exactly the display that I'm showing you exactly is to http:// bit dot, no, I'm sorry, no, bit dot ly slash, I don't want to go this way, so it's 2 lowercase h, capital H, capital L, capital G, 22. So if you type that in, did anybody do that already? Or if you try it and verify that you get the same display that we have here. So what I think I would prefer to do, rather than follow it in sequence, I'll let you do that when you look at it, is I want to quickly get to the single carrier OFDM, which is so different. These are just examples, like the first example was an 802.11. So here we have another example with the number, just the same ideas, the same concepts, but done for the purposes of LTE application. And in this case, notice that the data portion of every symbol in LTE is exactly 66 2/3 microseconds, and that's what dictates the tone spacing. It's the reciprocal of this number that dictates a 15 kilohertz spacing between tones. So there's a lot said about that, and remember when we're taking a look at this kind of a format that they have, that there are 7. They divide a frame into 10 milliseconds, and that has 20 subframe, 20 slots, and the 20 slots numbered from 0 to 19 are each a half a millisecond or 500 microseconds, and what a slot contains is either 7 symbols or 6 symbols. It provides for longer delay spreads for different regions of the country that might need them. And the beauty of the magic of if you're wondering why they have such funny looking numbers, 6 of these short cyclic, 6 out of the 7 short cyclic prefixes are this length, 4.69, and one of them is 5.21. And the reason is because they want this to be exactly the same in both the short and the long cases. So they basically force the slot time to be exactly 500 microseconds by a little subversion of what you would normally think there should be. A normalcy might be everything being the same, but they have to make one a little bit different in order to keep that exactly the same in both types. So notice that what you're looking at here is basically the formation of one of these symbols. Remember, a 7-symbol slot has 7 symbols. I'm just looking at one of them as just one of these lines. And so what you're seeing on this page here is if I took 3 of these symbols, then that's what you have here, symbol 1, symbol 2, symbol 3, and you got 3/7 of an LTE slot. So there's nothing conceptually different about OFDM here. It's just different numbers because you got a different application. And I've given you a lot of that numbering, but what I'd like to do is go to a different idea completely. And first of all, the motivation. Whoops. Okay. So on my list of questions about things we ought to know about digital communication is this question number 42. The major part of our evening has been in answering the first part of it, why OFDM is useful for high data rate fading channels, and essentially the answer to that is it turns out to be the easiest way to mitigate by getting an extremely simple equalization process, which is just multiplying by a complex number, it's just a benefit in implementation. And what benefit does single carrier OFDM makes in and why is it natural for mobile systems? So what you're going to see is that the uplink in a mobile system is generally single carrier OFDM, and the downlink from the base station is generally ordinary OFDM. So remember that when we were dealing with OFDM systems, we achieved robustness in the presence of multipath by transmitting on many different orthogonal frequency carriers, each operating, if this was M subcarriers, at 1/mth of the bits per second of the total bits per second. We partitioned, and that's all that we've been doing right now. Now, OFDM-A exhibits very pronounced envelope fluctuations. That is, you can almost get a sense of this. That if this is the real part and the imaginary part of one symbol transmission, or excuse me, of one of the gated sinusoids within this summation. Just think of having multiple gated sinusoids, and here's just a faster moving sinusoid, real and imaginary. So we're looking at one OFDM symbol, and we're lining, and in your mind's eye, maybe there are 500 subcarriers, and you're looking through those 500 subcarriers, and what you see is based upon the data, these subcarriers, and just line them up in your mind's eye, based upon accident alone, data choice alone, might add up to large amplitudes or very small amplitudes based on just the choices that you make. And here's a little example of such a, you can follow this, F sub 0 with this transmission, F sub 0 plus 15 kilohertz, or that's one step away is this phase, or another step away is this phase, or another step away is the blue phasor. You just take those values and you add them up, and you see that at one little region in time, there's going to be a null created. Now, this is just a little example to show. So you're going to have peak values and null values, and the kind of transmitters that you use in all radio transmission are the ones that really want to be operating at their peak power. They don't want to, you don't want to have to step back and reduce them because they happen to be very nonlinear at some point. And suddenly, what this peak to average power ratio that happens to fall in these, in particular, ordinary OFDM, is a real problem. So the motivation for reducing the peak to average power ratio, so power amplifiers are DC to AC converters, and power pulled from the DC power supply, which is approximately constant, not delivered to the load, is dissipated in the power amplifier. Amplifiers are very inefficient in their transduction process of turning DC power into signal power when they operate at small fractions of their peak power level. So backing off to be in a linear region and working at small fractions is terribly inefficient. Let's take an example. Typical efficiencies for an amplifier operating with an IEEE A0211A signal on the order of 18%. Thus, an amplifier required to supply 1 watt would have a peak power capability of 16 watts and would be pulling 5.5 watts from the power supply while squandering 4.5 watts, raising the temperature of its heat sink while delivering 1 watt to an external source. very inefficient. And that's why, particularly to maintain efficiency on the user equipment particularly wants to solve this problem. So notice we asked the question, what do we mean by basis functions? And a common mathematical representation of a signal is a linear combination of elementary functions called basis functions. They can be a variety of things. They can be, gated sinusoids are the gated functions in OFDM. Square root Nyquist pulses, the sinc functions, which also go by the founder's name, the Dirichlet functions, are basis functions. So in OFDM, the basis functions in the time domain are the gated sinusoids, and in the frequency domain, that's where we allow the coefficients of our data to dictate exactly what that sinc function looks like, because those basis functions are sinc functions in the frequency domain, and in the time domain, they're going to spit out gated sinusoids. But when we go to single carrier OFDM, it's just the opposite. The basis functions in the time domain are the sinc pulses, and in the frequency domain, they are gated sinusoids. Okay, let's get to some pictures. So when we're talking about gated sinusoids, and you see by accident of the random data alone, you can have just by the poor choice of, or just the accidental choice of data, a large peak followed by nulls and a large peak to average power ratio. The moment you change to different basis functions, like staggered sinc functions, you see the addition of these things. They never line up based upon what the data is, and it gives you a considerable improvement on, and we won't go into, but there's a lot of data on exactly what that improvement is, and it is considerable on what it looks like. So remember when we had pictures like this, which was the inverse DFT operation for ordinary OFDM, notice how it changes its appearance here with the single carrier FDMA. So let us show you that we have one important added step, and that's on the creation of these signals. This endpoint DFT this is the step that makes all the difference in doing this. Let me see if I can. Okay, so I think we're getting to the place where a pictures might help you. I think this is a useful picture just to keep in mind the concept of how they differ. So they differ because in ordinary OFDM, remember, we went in on this frequency axis with sinc functions that represented frequency information, and we came out with gated sinusoids. Now, with the single carrier OFDM, we have this extra step called a DFT. So with this extra step called a DFT, we're also going in with sinc functions, just as we did here. But remember, the sinc functions here were in frequency, and we went into this transform picture on the frequency axis. And here, this represents time samples, not frequency. And we're going in here on the time axis. And we're coming out of here with wideband simple signals. So each one of these outputs, you can think of it as this as the spectral picture of a gated sinusoid, because you see, you basically have in frequency spectral lines. This is tone 1, tone 2, tone 3, tone 4, and so forth. And you got a similar. The thing that really changes is the phase information. You know, the wideband changes very little, but it's just the phase information that's making it quite different. So this is the DFT output, which are frequency samples, and now you're going to go into this kind of a picture this is the same inverse DFT picture that we had with ordinary OFDM, but remember we preceded it with this operation. So now what our input is, these are still frequency samples as they are here, but they don't look like this. They are gated sinusoids in frequency, and look at what comes out in time. Our time samples out. And the beauty of this is that the time samples that come out are the same as the time samples that started off at the transmitter. And remember we said that we can never take the output of these sample points and sample them and get the original data. But we can here. Here these time samples are the same, you know, forgiving us for errors. There'll be some errors, but essentially the same as these time samples. So just sampling it will give you the output. Okay, so another picture that I find useful is the same frequency plot for DFT and IEEFT. So with the single carrier, I'm just showing it to you simplified with one picture, and start here. So you start here with input time samples going in to the time axis and coming out with gated sinusoids in frequency, wideband signals having different magnitudes and phases, magnitude 1, magnitude 2, and so forth. And then turning around and taking that frequency information back into here and coming out with the time samples, which are sync functions. So just conceptually, I think that can be a shortcut. Either one of those two slides can be a shortcut to keeping in mind the difference between what you're doing here. Let me, this too shows you the same picture that this is OFDM on top, where you're coming in with the sync functions that represent the coefficient information that's going to dictate what sinusoids get built. They get built here and put out as gated sinusoids, the superposition of which make for the output samples here. While in the case of single carrier OFDM, where this is the added step, the DFT, and you're coming in, look, the same kind of a function, but here it was in frequency, here it is in time. You're putting in time samples, going through a DFT that turns time samples into frequency information. Again, you've got magnitude, bandwidth, and phase information, everything you need to know about those superimposed samples. And now you go into the same IFFT with frequency information, but not this frequency information, this wideband frequency information, and out come the narrow impulses, wideband in, narrow out, comes the time samples, and they're staggered sync functions, again, precluding the high peak to average power ratio. And let me just do one. Okay. A single carrier OFDM symbol is not constant over the OFDM. Okay. Now let me read it here again. In single carrier, this slide says the same thing, but it's simpler here. In single carrier OFDM, the narrow sync function main lobes are misleading. See, misleading, I'll tell you why they're misleading. Because remember how we started off at 4:30 this evening? We started off by saying the magic of OFDM is getting long symbols, long symbols, long symbols. And suddenly this has got all of the attributes of OFDM. It's a variant of OFDM. It seems to the observer that it's got short symbols. Short symbol, where are the long symbols? So that's an important thing to keep in mind here. This is misleading. They appear to have short symbols, giving the impression that short symbols are sent. But just like OFDM sends the superposition of long-gated sinusoids, here too the single carrier OFDM sends the superposition of long these are long. You don't appreciate that they're still long, and they are cooperating with each other to peak up at staggered times. So I think we've covered the essence. I didn't imagine that I would be able to do it, but I think I covered the essence. Oh, there is one other thing I'd like to show you, and that's these slides here. Is there another way? For implementing single carrier off the M transmitter, why bother with DFTs and IFFTs when we just end up with samples of data carrying carried by sync functions? So the question came up by looking at this picture right here and saying, look, why bother with all these transforms, DFT, inverse DFT, when I just wind up with exactly the same thing here? Isn't there a simpler way of doing it? And that way is yes, yes, but. And, okay. Can we design a single carrier OFDM transmitter with just a sampler and a raised cosine shape? And the answer is yes, but. Okay, so here's what the suggestion would be. You take a data waveform and you sample it. And you get N sub C data samples for those N sub C subcarriers. And you're basically going to multiply it by an endpoint sampling sync function. And this is a digital RC filter. And the output comes out as samples of the sync function. No transform, no Fourier transform, no inverse Fourier transform, because when you get it at the receiver, you sample it. So, and the question, it looks easy, doesn't it? Two problems. The circuit performs multiply, accumulate, or convolution linear, not circular, causing loss of orthogonality. But we can handle that. That's not the main problem. Here's the main problem. The main problem is there is an excessive number of multiply operations. So would you have believed that all of this simply came about because it is the easier way to implement it? Multiply, if you count the multiply operations that we would do this way, they can be extraordinary. So let's take an example. For representing each sample point of an NC point data sequence, the sampling sync function needs to have n points providing the resolution in the frequency domain, and formation of each such sampling sync functions requires the scaling or multiplication by the data. So the computation involved multiplying n-point sync functions with nc data points, call it approximately n squared. This is, nc is a little less than n, but just call it n squared multiplications. And sync function symmetry, because the right hand and the left hand is the same, reduces that to 1/2 of n squared. And by using transforms, the number of multiplications is reduced to n log base 2 of n. And notice that for n much greater than 16, the difference starts to be extremely significant. For example, if n is equal to 1,000, n squared over 2 is 500,000, but n log 2 is 10,000. So more multiplies means more battery power. It's not just the matter of, somebody scribbling down more numbers. It means more operations, more battery power. Therefore, all of these signal processing steps came about simply because of the implementation benefits. So looking at this closely was a surprise to me, and I think, by the way, once you're online, you're going to need a password, and it's my last name followed by IEEE. And I know we're quitting late, and there probably isn't time. Well, you can hold me and talk to me about questions if you have them. But if you think of them later, remember my email address is on here. Students are always emailing. I encourage students to email me. Please do, and I'll be glad to answer your emails. Thank you very much for coming, and I look forward to some date in 2018 when I can finish up with a MIMO. Thanks. Thank you.